Okay, so this is a new screencast and a new version of this, the work energy problem notes. I adjusted problem 2B and 2C from what Mr. Woodward had. We're going to get the same answers, but I have rephrased them so you don't have to make use of a certain concept. In problem 2B, Mr. Woodward went ahead and used a principle called the conservation of momentum, which is what we're going to be studying in our next unit. He kind of introduced it early and he kind of just races through it. I'm going to explain it in a different way without using that conservation of momentum. And when we get to it, hopefully you'll see what it is. So but hopefully that will make some sense. So if you already did the problem as Mr. Woodward put it up, that's fine. We're not really going to need to know this stuff. You really need to just understand the concept of work. But I'm going to show you how to do problems 2B and C using just the concept of work and a sort of an axiomatic statement that you'll have to just sort of take on faith. So we have this mass here that's 15 kilograms, and we give it a push. And that push is some non-conservative work, some positive non-conservative work that puts 600 joules of energy into the system. We could say that we do some 600 joules of work to get 600 joules of kinetic energy that starts it moving. It also has some potential energy due to its elevation. And then it slides down, and that potential energy is converted into kinetic energy. So we're going to have the kinetic energy from this 600 joules of work plus the kinetic energy from turning the potential energy into kinetic energy as well. Okay, so we want to find the work energy relationship for the 15 kilogram box as it slides down the hill. So the initial state is at rest at the top of the hill, and the final state is just before colliding with the 9 kilogram box. So, we're basically doing this problem. We're sort of ignoring this second box for now. Not sort of, we are ignoring this second box for now. Okay. We want to find out what's the velocity of this box just before the collision. So the initial kinetic energy is 0. There's no kinetic energy when it first starts, but there is some potential energy because it's got that elevation. And we also do some work, which is positive. We push it in the direction that it moves. So when it gets to the bottom of the hill, there's no potential energy. So that means all this potential energy and all this work becomes kinetic energy. So that's the basic idea. So how do we find the velocity of the 15 kilogram box at the bottom of the hill? We can use the work energy theorem along with conservation of energy. So initially, right, we can always say the initial energy equals the final energy. And why don't we call it E1, right? Why don't we say this is E naught, when we're up here. Why don't we say E1 is when we get down here before the collision. This is before the collision. So the initial energy, this is E1. So the initial energy, initially there is that initial work, right? And I'm gonna go ahead and I'm gonna say that's the work, well, we just call it work 0, right? That's the initial work we put in, plus the potential energy we started with, and there was no kinetic energy to start with. So that's going to equal the kinetic energy at the bottom of the hill. And there's no potential energy at the bottom of the hill. And before the collision, there is going to be no additional work aside from this work that we started with. So we know this value we were just given, work initial, plus this is mg h initial equals 1/2 m v1 squared. And though we don't need it now, why don't we just get into the habit? Why don't we call this, we notice there's two masses, so why don't we call this one m1 and this one m2. So I'm going to go ahead and call these m1 and m1 because this is before the collision, before they combine. So we can find this value v1. We isolate both sides, got to multiply both sides by 2 over m1. And then that would give us v1 squared on this side, and then we square root it. So that would mean that v1 equals the square root of 2 over m1 times that initial work plus m1 g h initial. And then we just plug in those values. I'm going to move it up here. And so v1 equals the square root of 2 over 15 kilograms times that 600 joules plus 15 kilograms. I'm going to try to make these a little bit smaller so we have a little, can push them together a little bit more. Plus 15 kilograms times 9.8. Here, maybe I'll, sorry, it's a little cramped here. I'm just going to put the numbers. That's 15 times 9.8 times the height, which is 3. And when you multiply those all together, that's also going to be units of joules, right? Kilograms, meters per second squared, meters, that's going to make a joule. So we put that all together and we do that calculation, and we're going to get some result that is V1 equals, and I have to do that calculation myself right now. And I think it comes out to be something like 7 or so. I don't know. Maybe it's a little higher. I'm going to do it right now. So we have okay. So this comes out to be 11.7813 meters per second, which we would just report as V1 is approximately, these are really just given to 2 significant digits. So we would really just sort of report this as, maybe let's say if it's to 3 significant digits, we would say 11.8 meters a second. If we report to 3 significant digits. Okay. So that was part A, which is basically exactly the same thing that Mr. Woodward did. We're going to go on to part B, which is, this is going to be somewhat different here. So we know that V1 is 11.8. So let's go down here to part B, and I'm going to just clear the screen here. And I'm just going to make a note that we know that this V1 from our work, we saw that that was 11.7813 meters a second. In case we need that later, we'll do the more accurate version, and we'll just report it as 11.8 meters a second. So here's the part where we get to something that's quite a bit different. It says, determine the velocity of both boxes just after the collision. Mr. Woodward did apply the rule of conservation of momentum to figure out what the velocity was after the collision. And that's a concept we're going to study in a couple of weeks. But I'm just going to say that this collision, it does some non-conservative work. And if you think about it, hopefully it makes sense, because when the two things collide, it's going to make some noise. They also exert some force on each other. And the amount of work done in this type of collision, this is called a completely inelastic collision. In this type of situation is negative K1 times M2 over M1 plus M2. And why it is this value, that requires understanding conservation of momentum. But hopefully the idea makes some sense, because if you think about it, what does this mean? What we're saying is that that collision is going to take some kinetic energy or some mechanical energy really out of the system, right? And that's what this negative is here. So hopefully that makes sense. Also, what we're saying is that second mass, the bigger that second mass is, the more work is going to be done, the more energy is going to come out of that system. And hopefully that makes some sense, right? If M2 is really big, right? If that was a huge giant thing, it would really slow down M1. So if it was really big, it might take all the energy out. And if M2 is really small, then it's not going to do any work. And same thing, if M1 is really big, if M1 was really large, then it would just sort of roll right past M2. It wouldn't really make much of a difference if M1 is much bigger than M2. And if M2 is much bigger than M1, then it's really going to take a lot of energy out. So hopefully that makes a little bit of sense. And so hopefully now we can just say, all right, we can apply the work energy theorem now. So we know that we want to figure out what is the velocity of both boxes just after the collision. Okay, so just before the collision, we knew that we had a certain amount of energy in the system, right? So now we can say, instead of saying E0 equals E1, why don't we say E1 equals E2, where E1 is right before the collision and E2 is right after the collision. Okay, so E1, right before the collision, what kind of energy were there? It was just 1/2 mv1 squared. It was all kinetic energy, and it was only m1. But we know that there's going to be now, because of this collision, some non-conservative work that's going to be done. So that's going to be, in fact, here, maybe let's, maybe I'm jumping the gun a little bit here. We say E1 is just, there's going to be some kinetic energy, but there's also going to be some work done by that collision, which we'll call work 1. And then afterwards, there's just going to be the kinetic energy after the collision. So we can think about it like this. And then we can say, well, what is this? Well, we know that it's going to be 1/2 m1 v1 squared minus, right, minus that same kinetic energy, 1/2 m1 v1 squared times m2 over m1 plus m2. Right, that's the work that's being done during the collision. And that's going to equal 1/2. And now here the mass, we have to remember that the mass is now m1 plus m2. It's the two things moving together. And we'll call that v2 squared. And we can then isolate v2 here. This whole left side here, we can combine, we can just pull out, we can say 1/2 times 1 minus, whoops, 1/2 m1 times 1 minus m2 over m1 plus m2 v1 squared. Here we can put the, right, 1/2 m1 v1 squared times 1 minus m2, right? We can just factor this, right? This whole thing can get factored out, and then it's 1 minus this big thing, m2 over m1 plus m2 equals 1/2 m1 plus m2 v2 squared. And these 1/2s cancel. And we can then turn this, we can get rid of this 1 and just turn that 1 into m1 over m2. And then it would be m1 plus m2 minus m2. So it's just now it's just M1. So we can say, so therefore we've got M1 V1 squared times, if we make a like term out of that 1, we can say that's what, M1 plus M2, so it's going to be M1 over M1 plus M2 equals M1 plus M2 times V2 squared. So we could now isolate by dividing both sides by M1 plus M2. And then we just take the square root of both sides. And notice we got the same thing over here. We also have an M1 and an M1 here. So we can say, I'm going to move it down here to part C, and then we'll just sort of do some erasing and rewriting. So V2 equals, it's the square root of, what do we got here? We've got M1 squared, V1 squared over M1 plus M2 quantity squared. And that's going to be just M1 V1 over M1 plus M2, which is the same result Mr. Woodward had. So we can see that V2 equals M1 was 15 kilograms over 15 plus 9 kilograms. That cancels. And then V1 was that 11.7813 meters per second. And so that's going to give us 11.7813 times 15 divided by 24. This is going to be 7.3633 meters per second, which we're just going to report as V2 equals 7.36 meters per second, which is the same thing Mr. Woodward had. He just had, it might have been off by a slight decimal point. I think he was using 11.8 instead of 11.7 or something like that. So we have the same thing using this concept of just work, that this is the amount of work that is done by that collision. And that's the important thing to realize, that that collision does some work on the system. It reduces, there's some heat created by the compression of the two masses against each other. So let's go ahead, and I'm going to clear what we have here. And I'm just going to rewrite what we had here, which was that V2 is 7.3633 meters per second, which, we just report as 7.36 meters per second. So let's go on to the final part of this. And do it another color here. So now we want to do a bar chart to diagram the work energy relationship for both boxes as they slide across the concrete after their collision with each other. Okay, so we're looking now after the collision to when it comes to a rest. So after the collision, it has zero, whoops, not on the drawing part. It's going to have zero potential energy. It's got zero potential energy, and it does have some kinetic energy, which went down from where it was. There was the collision when it was up, where it was before the collision, it was up here at 5, and then we lost some due to the collision. We really should have done this analysis again up here in part B, but we didn't. Okay. But we just did the math here. So I'm going to say, so we're down here to this, we lost some kinetic energy during that collision. So we're here, and now we're going to lose energy again due to the friction. And why is it this much? It's this much because eventually, right, the final kinetic energy is 0, and the final potential energy is also 0. So that's why this amount here has to be opposite the kinetic energy. So what then is the nature of the force that is causing this? We have to remember that the force that is exerting this work is frictional. This is due to friction. That's the work due to friction. And I'm going to sort of go up here. Hopefully you remember that the frictional force is mu times the normal force. So we could call it mu k if we want to be precise, kinetic friction. And this, in this case, right, the box is just sliding across a surface. It's just a flat surface. So in that case, the normal force does just equal the weight. So this is just mu k mg. So that is the force, and then it is going to be opposite the direction that we're moving. So if we call to the right the positive direction, then the friction's got to be in the negative direction in this case. So what we have here, now we can say, all right, let's say E2 equals E3. And what types of energy do we have at E2? Well, at E2, we had the kinetic energy at 2 plus the work we do at 2, which is going to be the work from friction, equals, eventually there's 0 energy at E3, 0 kinetic energy, 0 potential energy. So this is 1/2 K2 would be M1 plus M2, the total mass, V2 squared minus the work, which is the force times the displacement. Remember, force, work equals F dot delta X. And in this case, the only force is the frictional force. So that's going to be negative mu k m, and the m in this case is the total mass, M1 plus M2, the whole thing together. So mu m g delta x, where delta x is the distance that this whole thing slides, equals 0. And this M1 plus M2 term can cancel. And so we have 1/2 V2 squared equals mu k g delta x. So divide both sides by mu k, divide both sides by g delta x to isolate mu k. Divide both sides by g delta x. And that's going to give us mu k equals V2 squared over 2g delta x, which is 7.3633 meters per second, the whole thing squared, over 2 times 9.8 meters per second squared times that 8 meters that it slides horizontally. And then we make that calculation, and that's going to be 7.3633 squared divided by 2 times 9.8 times 8. And that gives us mu k equals 0.3458. Remember, mu is unitless, which we would just report to 3 significant digits as 0.346. I think Mr. Woodward got something slightly lower, but that's just because of the way he was rounding. So we did it we worked the whole thing this way, and hopefully that makes some sense. Real quick, I just want to show, I'm going to sort of clear everything. I'm going to show how you could have done step C if you knew about this sort of thing in prompt B. We could have done that whole thing in one step if we understand that energy is conserved. So I'm going to clear everything. Just remember, energy is conserved. So what we could just, instead of going E0 to E1, E1 to E2, E2 to E3, we could just say E0 equals E3, or whatever, E0 equals E, anything. The point is, what's the initial kind of energy? The initial energy was, well, there was that work we initially did, the 600 joules, plus the potential energy when we started, the initial potential energy from the height. And then when we ended, there was no potential energy, no kinetic energy, but we also had some work we did during the collision, that's what we called work 1, plus some work that was done by the friction, which we could call work 2. And that would eventually all equal 0 because there was no potential energy, no kinetic energy at the end. So this we could then rewrite as work 0, that was the initial 600 joules, plus mg h0. And then this work 1, that was this term right here, minus K1 times M2 over M1 plus M2. And then this work 2, that was the work of friction, which was minus mu times M1 plus M2 times G delta X equals 0. So then the only thing we would need to know is, what is this K1? And that value K1, we know that had to equal this expression here, the work initial plus mgh naught. So we could just write that whole expression there, those two terms, we could sub those two terms in for K1. And if you wanted to do that, well, actually, I'll just go ahead and write it down here. We could say, so work naught plus mgh naught minus work naught plus mgh naught times m2 over m1 plus m2 minus mu m1 plus m2 times g delta x equals 0. And then notice we could even factor this out. We could say work naught plus mgh naught times 1 minus m2 over m1 plus m2. That would equal mu times m1 plus m2 times g delta x. So we could have, now we can solve for mu, right? Just by dividing these two things out. And, you know, it looks kind of complicated, but you would get the same thing. You get to the same exact place we got. So I hope that explains some things. I know it was lengthy, but if you wanted a sort of an explanation without conservation of momentum, hopefully that explains it. Thanks so much for your attention. Have a great 3-day weekend.